All right, good morning. So today I wanted to bring a show and tell. So I brought our USB spectrometer that we're going to use for the color lab. This is a whole spectrometer right here. It's a USB powered spectrometer, kind of like our Raman spectrometer, but even smaller. Our Raman spectrometer is a little larger. It's got higher resolution. But in here, you've got the light coming in. It's hitting it's focused directly on a grating, and then that grating splits the light, disperses the light onto a diode array detector. So you have like a camera element in there that has pixels on it, like 2,000. I think we might have 4,000 pixels on here because it's the USB 4,000. And then, you get a spectrum. So I thought we would play around with this. This is the spectrometer you're going to be using in the color lab that we're going to do next week. And so this is where we are. Or is it 2 weeks from now?
It's this week.
Oh, it's this week. So y'all have already been playing with this. Oh, that's right. There you go. So, all right. So anyway, what we've got here is we've got a fiber optic probe. Okay. And so this is what they call a bifurcated probe because it's got a single, it looks like a single fiber here that's split into. What we have is an illumination fiber, which comes out of our source, which is kind of hot. So this is our tungsten halogen lamp. So it's a bright light. It goes in here and it shines out of the center fiber. And then we've got 6 fibers around that fiber that go to our detector. They go to the spectrometer. So it's a reflectance probe. The light comes in, hits your sample, and then is reflected back at an angle other than the specular reflectance angle. So the specular reflectance angle would be the same angle from the normal as the illumination. So there's one angle that is specular reflectance, and all other angles are diffuse reflectance. So this is a diffuse reflectance probe, unless it's pointing straight down. Then it would be a specular reflectance probe right at the normal. Okay, so then we can take this probe and we can aim it around. Now the illumination light's just coming out of there. Can you see the white light coming out? That's pretty neat too because you're pretty far away from it. It's a tiny little source. That shows you the sensitivity of emission. So you can detect that light from quite a bit quite distant because your eye is looking for light. Absorbance is not as sensitive because you're looking for missing light. So you look at a bright light and then you put something in front of it and you say, how much did it dim? And the computer has a harder time with that. Whereas if you look at a black background, you see a tiny little LED light, then you get really good sensitivity. Think about your eyes at night when they're adjusted. You can walk around your house probably with just the lights from the power strips. These little LED lights that show you where the stools and the couches are. Okay, so this is our reflectance probe. And right now we're not seeing a lot because we're not getting much reflectance off of anything. But if I aim this, or let me put it on a white surface and we'll see the tungsten halogen lamp signal. So look at that. That is roughly the shape of the black body radiation curve that we saw at the beginning of the year. Okay, so back in September when we were talking about Planck's constant and Planck's law and his distribution, this is just looking at a hot tungsten filament. We use tungsten because it lasts longer. It's a very dense metal, very hard metal. It's very temperature resistant, got a high melting point. So we can make filaments out of tungsten and they can get really hot. Now the halogen part is we don't want the tungsten over time to sublime. So it's a hot metal. Some of those atoms are going to want to go into the vapor phase. And so if you put a gas around it, it holds the metal with that pressure. It holds the metal back on the surface. They collide with the gas and go back. There's a chance they'll go back to the metal surface and get stuck again. So it makes the lamp last longer. And then also it allows that tungsten filament to get hotter. And a hotter filament gives off more light. But that also means that the bulb, that gas will transmit heat from the hot tungsten filament to the glass of the bulb. And so we can't use Pyrex, we have to use quartz. Quartz is brittle. So if you touch that bulb with your fingers and get your fingerprint oils on it, it doesn't have a great thermal expansion coefficient. So the oils will cool parts of the bulb and not other parts of the bulb, and the bulb will break. So that's why you don't touch a quartz halogen lamp bulb with your fingers, because you'll get oils on there, and then the quartz shield will bust. So that will go bad. So we have this hot tungsten filament giving off light, and it's just a hot object. And so then you get this curve that's a function of temperature. So if we were able to use maybe a rheostat to change the current to that tungsten lamp, we might be able to cool it down, like run it at a lower current, and then we would see the maximum shift to longer wavelengths because it would be cooler. And if we could turn it up, we could move it to shorter wavelengths to make it hotter. So that's our black body radiation curve. We modeled that with a particle in a box simulation. But anyway, this is the visible region. Can't really see the. Let's see. Where'd my x-axis go? Oh, they're gray. The numbers are gray. Well, that's not fun. Okay. Huh. Yeah. So like here's 400. So I'll do it with my hands. This is 400 nanometers, and this is 700 nanometers. So this is red over here, and this is blue right here. So this is our visible region. So we got a lot of light in the visible region, and that's what we're going to be using this halogen lamp for, is to look at visible color. Now let's look at. So this is a solid object that's hot, and that's the kind of spectrum you get. Now this is a vocabulary word for you. Okay, this is called a continuum spectrum. A continuum spectrum because it has every wavelength represented. Okay, so when you have this nice smooth rainbow, when we had the Cheez-It spectrometer last time, we were looking around, we were looking at these tube lights. That's not a continuum spectrum. We're trying to get something that was hot and to show a continuum spectrum where you get the full rainbow, and this is exactly what we would see. This is a continuum spectrum. All wavelengths are represented. Let's aim this now at the tube lights. See that? That is not a continuum spectrum. That's called a line spectrum, because you see discrete atomic spectral lines. And so whenever they talk about the failures of classical mechanics, that word is used. They say the line spectra of atoms was not explained by classical physics. Okay, and to be honest, the black body radiation curve wasn't explainable by classical physics either. Classical physics was modeling this part, and it went up to infinity, and the UV catastrophe, because over in the UV, that line went back down to zero, and Rayleigh-Jean's law went to infinity. And so that was a failure of classical mechanics too. But the line spectra was a second failure of classical mechanics because they couldn't understand why the electrons doing the emitting and absorbing of light could only have discrete orbitals. They knew, their theory for spectroscopy was that something's jumping from a higher level to a lower level to give out light. Why does it not have any energy? If it has any energy possible, then you'd have a continuum spectrum. But you don't have a continuum spectrum. So we have line spectra for atoms. You get line spectra from atoms because they're in space and they don't have anything that's going to smear those energy levels. You have something as a solid, every tungsten atom, you got tungsten atoms at the surface, some that are just below the surface, some that are at different temperatures. You have all of these solid atoms emitting the light, and they have all kinds of effects, vibrational modes, acoustic modes as the filament expands and contracts and vibrates. All of those things smear the atomic levels of that tungsten element, and that's what's causing this to be a continuum spectrum. Because if it's in a solid, every little atom in that solid has a slightly different environment. And so all of its energy levels are smeared out. And so it goes from a line spectrum, when you go to a liquid or a solid, it goes to a continuum spectrum. So hopefully this is a good little primer on those two different types of spectra. Continuum spectrum has all the wavelengths of light represented, typically coming from solids and liquids. Condensed phases is what they call them. And then line spectra come from gaseous phases. We see that even in molecules. So your carbon monoxide lab, those are line spectra of the rho vibrational lines. So that's a different thing. Now, when we look at this spectrum, can I get you to aim this at that light so I can talk about it? You can stay in your seat, I think. Okay, there we go. Just give us a good bright signal. Aim it at one of those lights. So see where the metal is pointing? Yeah, point that metal probe at one of the lights. Point the probe, the metal probe. See the silver part? Yeah, aim that stick right at that light. Keep adjusting until it gets bigger. Yeah, better. Okay, that's pretty good. Let me zoom in. Let's see. Oh, my goodness. What's that say? Zoom out, zoom in, zoom out. Let's go right here. All right, let's go right here. We could go onto the NIST spectral database, and we could see if I can drag this thing down. Yeah, and we could see what all of those little bumps are. Okay, but those are, the spin-orbit coupling, most likely, of this gaseous atom. So you've got an orbital that has a certain L, certain set of term symbols, and then you got the spins of the electrons in there, and you can put them all, spin up, spin down, some combination of those, and that gives that hyperfine splitting of the J values. So when we do the term symbols, we might have like a three unpaired electrons. So you might have a quartet, and it might be in a G orbital, and you've got some combination of the L plus S to give you the different J values. And then you end up with a bunch of peaks that are possible that are very closely spaced. And so this hyperfine splitting, they call it, is related to the spin of the electron. And so these signatures, if you see this pattern, you know that this is mercury. So it's not that it's just the wavelength of a single peak that tells you it's mercury. It's the pattern. If you see that pattern in an emission spectrum, you know it's mercury. And so you can look at stars that you could never get to, okay? We can't really, I know it's great to think about going to Mars, but that's a long way away, and that's just Mars, okay? We don't live long enough to go outside of our solar system. So we'll never make it to the stars. I never say never, but I'm saying never on that. If we're right about the speed of light, then that's just a hard pass. We're not close enough, even if we're going the speed of light, to get to another star. Okay, so the spectroscopy is the only way we can get information from other stars. And if we see that pattern in a star, we know it's mercury. Now you might say, of course, because it's got a particular wavelength of light, 440, but no. If that star is moving away from us, then those wavelengths of light, when they get to us, look like they're going slower. Because if I'm emitting light and I'm backing up, it looks like a longer wavelength. Okay, and so that red shift of those stars causes all of these wavelengths to shift towards the red because they're moving away from us. And so this whole pattern will shift towards the red, but we see the spin orbit coupling and the patterns of highs and lows, and we know it's mercury because it has all of those lines. And so we know when we look at those stars as they're moving away from us, we might be in the infrared and we might see this same pattern. And we're like, wow, that's in the infrared, but it's the same pattern as mercury. It doesn't match any other element. And so we know that that's mercury, and we can calculate the shift of those wavelengths and see how fast that star is moving away from us. So that's how we map out the universe and understand how it's expanding. So you may have seen, or read about the red shift of the stars in the universe, and that's exactly what they're talking about. Let's play around. Let's play around with this a little more since we're here, and you guys are in. How many are in instrumental? Raise your hand. Okay, almost everybody. Okay, let's have some instrumental fun. You want to? So let's rescale this thing. Okay, so nice. It's a nice clean spectrum. Let me adjust my parameters here for a second. Okay, so I'm going to come over here to the data acquisition window. I've got it cleaned up because I'm averaging a bunch of spectra. So let me undo all the stuff that cleans up the spectrum. Okay, there we go. And Notice how it's much more active. It's like it's buzzing. Let me, how do I close this? Okay, there we go. You see, it's quite a bit noisier now. You see that? In fact, let's put it on the black surface so you can see what the noise level is. Yeah. So that's it's on a black surface, and so this is just the noise. 100 plus or minus 100 counts. So peak to peak, 200 counts of noise. Okay, where's that coming from? Instrumental people. Okay, it could be, but let's take the light source out of it. So I'm going to move this. I'm not going to aim at anything. So it's not really looking at the light source anymore. So we kind of ruled that out. So it could have been. That's right. It could have been. But when we remove the light source, essentially, we still have the noise. So if it's not the light source, what is it? Other option. Well, I guess there's two options: the fiber or air. Okay, it's air and air, or what else? What are we using to see in this setup? The detector, exactly. Okay, what is the detector? It's a camera element. Okay, we want it to be sensitive, meaning we want it to give a signal anytime it sees light. One of the ways you do that is you turn up the voltage between whatever diode it has. And so if a tiny little photon comes in and tickles that, it gives a signal. So we've cranked up the voltage on that detector to make it sensitive. Okay. And temperature fluctuations in the detector can cause false signals. So this is just temperature. The detector is at a certain temperature and it's detecting plus or minus 200, counts of just signal, from the thermal temperature of the detector. We can cool that down. We can put it on a cooling plate and reduce that noise. So the temperature of your detector is one of the things that can give you noise in your spectrum. Okay. Also, every little pixel is slightly different. And so you see pixel to pixel noise. And so one way we could do that, we don't really need 4,000 pixels. It's great that we have them, but we don't really need 4,000. So let's average every 3 pixels, we'll average those 3 pixels and plot that data point on the middle pixel. And then we'll move over and we'll average the next 3 and we'll plot them on that middle one. And then we'll move over and take the average of that 3. So that's called a boxcar average. It's like a train. You've got boxcars that move along. Only these boxcars overlap. You got a boxcar that's 3 points, and then it overlaps the next 3 points, and it overlaps the next 3 points. And you can come over here in the spectral acquisition window, and you can pick boxcar average right here, and you can go 1. You could do 2. I don't know which one you plot it on, but you could do 2. You can do 3. Look at the noise. Isn't that cool? 4, 5, 6. You see how it's cleaning up a little bit? Yeah. So that's boxcar averaging, and it reduces your noise. But eventually, you start to flatten out your peaks. So let's aim this up at the mercury vapor lights. That's pretty good. There we go. Okay, and let's look at this peak right here. You see that one bouncing along? Okay, I'm going to increase the boxcar. Whoa, what's happening to it? It's flattening out because the very top one I'm averaging with the ones next to it, and those are downhill. And so I'm flattening out my peaks. I'm taking the resolution of the spectrometer and reducing it by deleting pixels. Not really deleting the pixels, but I am averaging 20 pixels together. And so essentially I'm taking a 4,000 pixel detector and making it if I did 10, I'd be making a 400 pixel detector. Okay, so that has an effect. So don't overdo the boxcar averaging. I like to do 3 or 5. I like to do odd numbers because conceptually I can picture that in my head, but it doesn't really matter at all. Okay, it's bouncy. Why is it crazy? Crazy bouncy is because my integration time is really short. That's another thing that can cause you to have noise, is you're not looking very long at the data. So you see something, you're taking a quick snapshot, you're getting lots of noise. So let's look longer. So 50 milliseconds, let's make it 100 milliseconds. Okay, our signal grew, as you might imagine, because we're looking longer. Okay, so let's go back here and scale it again. Look how much cleaner it is. So you integrate longer, your signal to noise goes up. Your signal grows, but your noise doesn't grow very much. So your signal to noise improves with the longer that you look. That's certainly a principle. Okay, let's go to 200. Grew even more. So we can get really good signal to noise with this spectrometer if we look for a long time. Isn't that nice? Okay. But notice eventually we're going to saturate our detector. So we're going to look so long that we're going to blind the detector. The diode array, we call them bins. So every little diode is a bin, and it can contain so much signal. Okay, and so if we average for a long time, meaning we look, not average, if we look, we integrate for a long time, we're filling up that bin with signal, but the bin is only so deep. And so eventually, if we increase the integration time, the bin will fill up and it'll peg at the top. And so let's look at this tall peak here. We're going to try to saturate this signal. Well, we might, if I just aim it. Yeah, let's go to, what's this one? Set to maximum. Yeah, see, it's flat at the top. See, we're saturating. See, the bin is full. And that tallest peak is pegging the detector. And so that's called saturation. The bin is completely full. It can't hold any more signal. That's the simplest way to think about it, right? Each little bin, detector bin, has a certain amount of signal that it can hold. When you fill it up, it won't. No more will go in there. Okay, so that's spectral saturation. So you can increase this integration time until you start to saturate the signal. We see that also if we do the tungsten lamp. It's pegged. Look at that. So we can't integrate for that long with the tungsten lamp. So we're going to have to cut it back to 50, and that's why it was at 50. So what if we wanted to get good signal to noise, but we can't integrate? Then we average scans. And so we take a scan, and then we average the next one, then we average the next one, and that will help us reduce the noise. But we don't get an increase in the signal. Okay, what we're doing is we're decreasing the noise, not increasing the signal. Integration time increases the signal and the noise, but the noise increases less. Averaging keeps the signal where it is, but you cancel out the noise because you're averaging it out. And if the noise is random, then it'll disappear. And so that's boxcar averaging. So this is essentially taking, in measurements. Let's go over here and scale it. Let's see if I can look down here. Look right here. Let me take away the boxcar average. So that's the worst situation. And let's see. Stop averaging. Okay. There's our noise level. You see that? Can you see that pretty well? Okay. So then we start averaging that noise. 2, 3, 4. So if we average 4, the noise goes down. It's noise is proportional to 1 over the square root of the number of samples you take. That's one of the equations you learn in instrumental. And so as you increase the number of samples that you're averaging, take the square root of that, and that's the factor by which you're dividing your noise. So I've averaged 4, so we should be dividing our noise in half, 1 over the square root of 4. We could go up to, I could just do this at 9. Now we're dividing our noise by 3, 1 over the square root of 9. Okay, we could go up to 16, and we've been dividing our noise by 4. Okay. And it takes 16 times longer because we're collecting 16 spectra, and then we're averaging those. So the first time we have to count up 16, and then from that point it's a running average. So it's always averaging the last 16 spectra. And our noise has decreased. So that's That's another way to decrease your noise. So we could increase the integration, which increases the signal and the noise. We could average spectra, which just decreases the noise. So this is how you get a good clean spectrum. Okay, so let's move over to the lecture notes on our stellar spectroscopy. Okay, good. And so this is with this spectrometer, I aimed it out the window at the sunshine, and I saw this spectrum, which I thought was fantastic. What do you see here? You see the continuum spectrum. That's the broad shape. Does everybody recognize that now? Same as our tungsten halogen lamp, but it's at a different temperature because the sun is at a way different temperature than this tungsten halogen lamp. Thank goodness. Okay, so we get a lot more light, you know, in the 500s and 400s. Okay, in terms of our counts, and then, but if we look at that, we see dips. We didn't see those dips in our tungsten halogen lamp. So we're looking at these dips right here. So these are known as the Fraunhofer lines, these dark lines in the solar spectrum. So as soon as they started looking at the sun with the prisms and spectrometers and so on, they started to notice that there were some missing atomic lines, some atomic absorption lines, and it's named after Fraunhofer. And you see these are identified. And so A and B, these two big dips, so that's a large absorption right there in the visible spectrum. What is that? Well, they've determined that pattern matches the pattern for oxygen. So that's interesting. These two right here, A and B, are oxygen. C here is hydrogen. Well, that's interesting. Okay. D is a sodium doublet. We just talked about the spin-orbit coupling, and that doublet is clearly sodium. That's the same wavelength as sodium. And then over here, E is iron. So that's strange. It makes sense that as the sunlight comes into our atmosphere that we see oxygen absorb some of that light. But sodium and iron, there's no iron in our atmosphere. I mean, maybe if I'm welding, okay, and you were to do a spectrum, you would see iron, but you'd probably see an emission line from iron, not an absorption line. And I don't think there's enough people welding on Earth right now to get enough iron in the atmosphere for us to see absorption lines of iron in our atmosphere. So where's the iron coming from?
Just something in between here and the sun.
Yes. And there's really two options, our atmosphere or the solar atmosphere. So it's the solar atmosphere. We're looking at the iron and the sodium content. We also don't have a lot of sodium vapor in our atmosphere. Good. Thank goodness. It hurt our lungs quite a bit. And it's so reactive with water. As soon as on a humid day, there would be no sodium in Huntsville's atmosphere. Okay, so, and I got this in Huntsville. So we know it's not sodium. Now maybe it's up above the clouds, but no, it's not. It's so far above the clouds, it's on the sun. So that's what's going on with these Fraunhofer lines, is you have the solar ball that we see, the visible corona ball, the sort of the surface, we call it the surface of the sun. That's the last shell of the sun that's emitting visible light. That's what we see. But what we don't see is this outer ring here. There's an atmosphere around the sun of ejected atoms that have been ejected, but not with enough force to cause them to escape the velocity, have escape velocity of the sun. Okay, so they're captured by the gravitational pull of the sun. So they're orbiting or flowing around the sun. Maybe they've collapsed back into the sun and so on, but more gets ejected out. So there's this stable atmosphere around our sun. And then as it's emitting light, like there's a sodium atom up there. And then as that light goes past that cold sodium, once it gets out there, that sodium atom finds an electron, pachinko, emits the light. And now we've got a ground state cold sodium atom, and this light hits it, and that sodium absorbs its sodium line, the S, the doublet S 1/2 to the doublet P 3/2 and the doublet P 1/2. So we have that doublet absorption, and then it comes all the way to Earth, takes 8 minutes to get here, okay, hits my blinds in my office and goes into my spectrometer, and I get that that earlier spectrum, minus a little bit of the light from the sodium. And we know it's sodium because it has exactly the same intensity pattern as sodium does here on Earth. Okay, so we know it's exactly the same wavelengths, the same doublet. That's important. We see these signatures of elements, and we can learn something about the stars. And so we can do this for all of the stars. I've shown you that before, and all these different, we put these on satellites, we put them on our terrestrial telescopes too. And so this is this is how we've mapped out our universe. This is the standard cosmology model. Now this, have you ever seen this picture before? You never seen this picture? Okay. Okay. So if you have, okay. So it's hard to show the expansion of the universe in 3 dimensions when you add a 4th dimension of time.
Yeah.
Okay. So you would need a video. Okay. We have videos, but this is an attempt to do that. So they've taken away one of our spatial dimensions. So let's say they deleted Z and made that time. Okay. So time is going this way, and then this disk is representing our spatial time. So like X and Y. And so it's kind of like the surface of a balloon as it expands. And if you put like a couple of dots on a balloon and blow it up, they'll move apart. And so that's what's being shown by this cone. So this you see this expansion. It's talking about expansion here. You see this cone is expanding here and here. So that's showing the expansion of the universe, because like these 2 objects got further apart as time went by. Okay. Now, when we do astronomy, let's say this is our galaxy, and somewhere in that galaxy is our solar system, and somewhere in that solar system is Earth, and we're looking at the stars. We can't see that star because we can't go in an instant, same time, and see that star. Every time we look at a star, even our sun, we're seeing 8 minutes, the light it emitted 8 minutes ago. And if we look at a star that is a million light years away, we're going back in time to see that star a million years ago. And so if we look at a different star that's further away, then we're looking back in time further and further and further. Now, it's incredible. Our universe, apparently, if we look between all the stars, we can look back and we see this cosmic background radiation that's about 13.7 billion years ago, right here. Okay. So that's pretty cool. We can go all the way back to what they call the cosmic afterglow. Now, why is it in the microwave region? Well, because we're expanding so fast that bright light that was in the visible and UV and X-ray and gamma ray region, we're moving away from it so fast that it looks like it's in the microwave region because of this Doppler effect. Okay. So we see things shift more and more red the further away we are. And so all of the wavelengths of light are shifted. Now we can see this pattern, especially in like the sodium lines and all of these lines that are well characterized, the spin orbit coupling, and we can look at these different stars and kind of map them out. So now this initial inflation is the thing, they say quantum fluctuations, but that's not even close to being resolved. So that's why I put a big question mark there. We don't know what force caused the universe to rapidly inflate at the beginning. Okay. And so there's lots of philosophical and theological speculation about that. But notice the abrupt slope of this inflation. It's way greater than the speed of light. So that kind of breaks physics at the very beginning. So we don't know how that happened. Okay, so let's look at this evidence for the expanding universe. It's the cosmological redshift. So here's the sodium line. And you see, if you look at a star farther away, you see the same sodium doublet, but now it's shifted. It's not at 589. It's now at 591 and 592. So they've slipped. So we're looking at this star, and we see the redshift. Now, this was predicted by Einstein, and then Hubble went and measured it. And he was like, whoa, it actually exists. So you hear about redshifted light from distant galaxies Now you know what they're talking about. It's the atomic lines that are redshifted. We know it's a sodium line because of the doublet, and it's been redshifted. So it's not that the star just looks red. I mean, it does, but it's also particular atomic absorption lines that have been redshifted. And so here's the math. You could calculate the wavelength on Earth and the wavelength observed, and you could get this Z value, this redshift value. And it's a nice percentage. It's like what percentage of the wavelength has been elongated, you know? So it's the difference over the wavelength. Yeah. And so then there's an equation that can tell you the velocity of that expansion. So if we take that percentage and multiply by the speed of light, then we could get this kilometers per second. That's how fast it's moving away, because you convert the wavelengths over to kilometers and so on. Okay. And then Hubble's law takes this velocity and connects it to distance. Now, this is a very interesting thing. If we look for stars that have the same iron content as our sun and compare their brightness, there's different sizes of stars. So we can find stars very similar to our sun, and then we can see how far they are away from it. If the star is the same size as our sun, it's going to be the same brightness. Okay, be the same temperature. And so if it's dim, and it's got the same iron signal, we know it should be as bright as our sun, and it's dim because it's farther away. Okay, so we can map out our near galaxy, or our near stars in our galaxy using parallax. Now, what is parallax? Well, your two eyes. That's how you measure depth for close objects. Okay, I get two different pictures from my two eyes, and I can compare those, and when they don't overlap, I give them depth and they overlap. We can do that with our telescopes too. So in the spring, Earth is over here. Take a snapshot of the universe. And I wait till the fall. Okay. And I wait till my telescope turns around and I see the same field of view and I take a snapshot of the universe. And then I've got two eyes that are separated by the orbit of Earth, and I can find stars similar to mine, and I can come up with this brightness distance calculation. And that's a way to map out that, yes, this brightness for stars that are similar and distance are correlated. Then we can look at the redshift, and we can come up with this equation. The redshift and the distance is a linear relationship with some noise, okay? But it's a pretty linear relationship, and that's Hubble's law. And so that gives us this 1 megaparsec. A parsec is a real thing, okay? 1 megaparsec per year. And so it's 3.26 light years is a parsec. And so this Hubble's law, this constant here, gives us a distance here in light years and a velocity. So if we could calculate the velocity from the redshift, we could use Hubble's constant to get the distance. And it's funny that, this uncertainty right here, these little stars, half of them are above and half of them are below because that's a galaxy and it's rotating. So we're not just getting the distance and expansion from us. Some of those stars are coming towards us and some of those stars are going away from us. So that's a rotational effect, which causes that little cluster. So we can practice here. What would be the observed wavelength of the sodium line from a star 20 megaparsecs away? So here's our equation. We've got distance. It's this redshift equation, the speed of light, and Hubble's law. So we could rearrange that to get to the observed wavelength. And so here's our math. It would be 592.4 nanometers. And so we could very, very carefully know like how far away that star is, or that the star is in a particular galaxy. And then when did that light emitted from that star? 20 megaparsecs away. We know a parsec is megaparsec is 3.26 million light years. And so this is 20 of those away. And we can just multiply that by 20. And that left that star 20 million years ago, went through space 20 million years, and just happened to go into our telescope. That's just crazy to think about. But, these things are emitting light in all directions. We look at them and we're looking back into the past. And so that's one thing I love about astronomy. So you're actually looking at the past, at every star that you see. So how many meters is that? Well, light year is 3 times 10 to the 8 meters per second. Okay. And so that's roughly a mole of meters, 6 times 10 to the 23rd meters away. That's a long distance. So this is how we've mapped out these stars, and it's pretty amazing. We've seen a lot of things with our space telescopes, most recently the James Webb Space Telescope. We've seen over the years many examples of gravitational lensing, which is where the gravity of a black hole can bend light. And so we can find supermassive black holes in space by looking at distorted images of the same galaxy that are on both sides of this hole. So we have, let's say we have a galaxy here, and a black hole here, and Earth here. So we're looking at the black hole, and around that black hole up here, we see this galaxy's light got bent towards Earth. And the same exact galaxy gets bent this way towards Earth and hits our telescope. And we've seen some really crazy images of twisted galaxies that have been deflected by supermassive black holes that are out there in space. So it's a pretty great time to be alive to see some of these tools. And one of the ways you would determine if those galaxies were the same is, one, you could computer model the distortion from the supermassive black hole, and you should be able to recreate the visual image of that galaxy. But another thing, too, is using atomic spectroscopy. You would look at some of the signals from the same objects in those two galaxies and see if they had the same atomic spectra, the same amount of mercury and the same amount of iron and the same amount of sodium and so on. So that's how we've pieced everything together. So a lot of this material was taken from physicist Michael on YouTube. You can go there and see his video where he explains it. It's great stuff. And so this is just evidence that, this physics has been the same using this spin-orbit coupling. We know that the splitting and relative intensities have not changed in the spectra because we see the same doublet. Let's just use sodium. The same sodium doublet just moves redshifted by redshifted as the distance of the stars gets further away. We don't see a time anywhere in the past where all of a sudden physics has changed and that doublet switches or changes its splitting or anything like that. It's just a smooth transition all the way as the stars get further and further away. So hopefully that was interesting to you. There's more of an enrichment day of just kind of talking about spectroscopy, helping you out with instrumental, some of the terms, and then getting you ready for this week's color lab.